This video is a presentation and demonstration of cooperative dynamic spectrum access in the Cosmos wireless testbed. It was prepared as part of the research activities conducted under a planning grant awarded by the NSF in its Spectrum Innovation Initiative program. Researchers from 3 different universities collaborated in this work. This is the research team. Dragoslav, Prasad, Ivan, and Dipankar are affiliated with Rutgers University. Igor and Gil are with Columbia. And I am Carlos, and I'm affiliated with Syracuse University. Throughout this presentation, you will also hear from Dragoslav, Prasad, and Igor. Our team has been working on methods to enable cooperative dynamic spectrum access interactions between wireless devices. We decided to tackle this problem starting from an information architecture perspective. One of the elements in our information architecture is the use of a standardized data model to represent the boundaries of spectrum used by any transmitter or receiver. The data model we are using are the spectrum consumption models standardized under IEEE standard 1900.5.2. By the way, I am a member of the IEEE workgroup that has been working on this and other standards related to dynamic spectrum access. SCMs provide a set of constructs to express how a device uses spectrum either actively or passively. The standard for SCMs also provides a means to compute if 2 or more devices that have shared their SCMs will interfere with each other or not. This is called the compatibility computation. The way the computation is done relies only on the information in the SCMs with no other dependencies needed. The constructs defined for SCMs can be used to build transmitter or receiver models. These in turn can be combined into aggregate models, and such combination can simplify the execution of compatibility computations. Additionally, SCMs can also be used as the elements to write simple authorization or constraint policies that can be used in dynamic spectrum access scenarios. For the context of this presentation, we will only use transmitter or receiver models. Transmitter models express the way an RF transmitter device will radiate RF energy and how that energy will propagate. Receiver models describe what is incompatible interference and capture the spectral sensitivity of the receiver. Now, Dragoslav is going to provide some initial details on the implementation of the cooperative dynamic spectrum access scenario that our team worked on for this presentation.
In 2016, DARPA started the Spectrum Collaboration Challenge, an international competition which engaged multiple teams who built collaborative intelligent radio networks, or CERNs, with a mutual goal of increasing their spectrum usage efficiency through collaboration. As part of the challenge, DARPA, together with all the competitor teams, designed an interaction language which enabled the radio networks, or CERNs, to exchange information. The language was named SIL, which stands for CERN Interaction Language. SIL was implemented as a pub subservice for several types of messages. Our framework uses a network interaction language heavily based on SIL, with some adaptations. Mainly, instead of SIL's exchange of spectrum voxels, our framework enables the exchange of SCM messages, allowing for a standardized and more detailed description of intended spectrum utilization. Just as in SIL, the message exchange protocol is implemented using Google's protocol buffers to minimize the transmission overheads. The figure shows the scheme of the language. Each network uses a designated node, the wireless domain controller, to interact with other networks. The interaction is controlled by the collaboration server and runs over Ethernet links. Our network interaction language supports several types of messages. A register message is used by a wireless domain or a WD controller to register with the collaboration server. A newly registered peer will be informed of other already existing peers with a series of inform messages. The existing peers will in return be notified about the new peers with a series of notify messages. SCM requests are used to request spectrum consumption information from other networks. After receiving an SCM request, a network will respond with an SCM message. Upon receipt of an SCM message, a network will run compatibility tests to determine whether it can coexist with another network in the same bands. It will then set its radio parameters accordingly and send its compatibility test report to the other network. Calibrate radios messages contain measurements used by networks to calibrate their SDRs with specific parameters. When a network finishes its intended communication, it will send the leave message to the collaboration server. This figure describes the protocol used by the networks to join, determine the wireless communication parameters, and leave the system. At time t1, network 1 joins the system and its WD controller sends a register message to the collaboration server or the regional controller. The regional controller then sends an inform message containing the list of all existing networks. This list is currently empty. It's time t2, network 2 joins the system, and we can see the register message sent by WD controller 2 to the regional controller. It is then informed about all the existing networks. This list contains only WD1. WD1 is then notified about WD2 joining the system. WD2 will then request the SCM from WD1 and immediately receives it. WD2 then runs its compatibility test and reports the result to WD1. Both WD controllers now configure their radio parameters based on the compatibility test results. When WD1 decides to leave the system, it will send a leave message to the regional controller. The regional controller will then notify WD2 about the list of all other WD controllers, which is now empty. To better understand some of the basic components of the algorithms we are researching to allow wireless networks to determine their radio parameters, we can take a look at the flowchart shown on the slide. When a new wireless domain joins the system, it will initially assume it can operate under its default radio transmission parameters, such as the central frequency, bandwidth, and power. The new network's transmitters will then run compatibility tests against all existing receivers, and the new network's receivers will run the tests against all existing transmitters. The network or the wireless domain will then evaluate the results of these compatibility tests. If any of the test results show that the default transmission parameters would cause interference to any of the existing nodes, the wireless domain will select different parameters, which result in avoiding all the interference. The SCMs of the wireless domain transmissions will be updated accordingly to be sent to other wireless domains upon request, and the links are then established. It is worth noting that all of this is an explanation of one of the most simple algorithms to achieve coordinated spectrum use among different wireless domains. Other parameters, such as transmit power, could also be used. We will describe some of our ideas for future coordination algorithms later in this presentation. Now, Prasad will discuss and show a demo of the implementation of cooperative DSA on Cosmos based on the elements presented so far.
We have a ZMQ server, which acts like a regional topology manager, maintaining the list of wireless domain controllers in the system. The messaging is performed through a push-pull mechanism. At time t1, wireless domain 1 enters the system and registers with the ZMQ server. Since it is the only domain in operation, the nodes in the domain can confidently set up the communication link using the default parameters. At time t2, wireless domain 2 shows up, registers with the server, and receives SCM from WD1. Once the SCMs are received, it carries out compatibility computation against them, and based on the result, it determines the operational parameters for the link in its domain. At time t3, wireless domain 3 shows up, it registers with the server and receives SCM from WD1 and WD2. Based on the compatibility analysis result, it determines how its node should operate to set up a link. We are using orbit grid component of the Cosmos wireless testbed to perform these experiments, and the node mapping is shown on the slide. The figure shows the orbit grid testbed present at WinLab Rutgers University. We have used 3 links in our experiment, and all these links have a high probability to interfere with each other if they operate on the same channel at nominal power levels. We have a set of different channels that the devices can choose to operate in order to avoid interference. There is also sensor node present at node 3.1 to capture spectrum occupancy. Now we'll go through the process of setting up each link and seeing how the cooperative dynamic spectrum access takes place. The figure shows link 1 setup from node 320 all the way to node 24.5 on the MIMO rack. Here, we start WD1 using the following script. It sends a register message to the server to associate with the collab network. There is also keep-allow messages being exchanged to keep track of client WD1. Since there are no existing clients, WD1 starts transmitter and receiver with default center frequency of 2000 MHz. We observe the transmit signal being captured by the sensor node and packets being received by the receiver, confirming link 1 setup. The figure shows how link 2 will be set up from node 18.1 to node 24.11 on the MIMO rack. Link 1 is currently active as described before. Here again, we run the same script as before. WD2 exchanges the register message with the server. The server notifies it about the existing client WD1. It requests for the SCMs from WD1, and upon receiving it, WD2 performs compatibility tests between its own transmitter and existing receiver, and also between its own receiver and existing transmitter. This shows the SCMs being received by client WD2 from WD1. The new spectrum and underlay mask is shown on the slide, and since the radios are not compatible with each other, a new frequency different from 2000 MHz, which is in use by WD1, is selected, and the corresponding transmit and receive nodes are started with the selected frequency. We observe the spectrum at 1999 MHz and also packets being received at WD2's receiver. The figure shows how link 3 will be set up from node 814 to node 23.5 on the MIMO rack. Link 1 and 2 are currently active. When we start WD3, it registers with the server. It also gets to know about the existing clients WD1 and WD2 present in the system. WD3 requests the SCMs from WD1 and WD2, and on receiving the SCMs, it performs compatibility tests between its own devices and existing devices in the system. We have here in total 4 tests for compatibility. Based on the compatibility report, a new frequency is selected and the respective transmitters and receivers are started. We observe on the sensor node that WD3 set its link to operate at 2001 MHz. Also, packets are receiving at WD3's receiver. Since WD3 consists of B210 USRPs, we also observe out-of-band interference, and we plan to model this interference with SCMs in future experiments. This concludes the demonstration of our setup, illustrating the use of SCMs to build coordinated dynamic spectrum access among a set of wireless networks. Now Igor will talk about some of our future work ideas.
In future work, we plan to develop centralized and distributed spectrum allocation algorithms and implement them in the Cosmos testbed using the SCM data model. In this slide, we display an ideal algorithm that achieves optimal performance. In this algorithm, a centralized edge server keeps track of the status of every radio in the network. When a disturbance occurs, for example, a new radio enters the network or an external radio starts to interfere with the network, then this disturbance is communicated to the edge server, and the edge server computes the optimal allocation of spectrum and power in the entire network and communicates the new configuration to every radio in the network. Clearly, a main challenge associated with this algorithm is the high computational complexity associated with computing the optimal resource allocation of all radios in the network. Another important challenge is the transient cost of reconfiguring the network. Each radio will implement the new configuration when it receives the command from the edge server. Notice that some radios may implement the new configuration while others are still operating on the old configuration, and this may cause transient interference. Both the computational complexity and the cost of reconfiguration are important parameters that must be taken into account. To reduce the computational complexity, a more realistic centralized algorithm is one that uses greedy or machine learning-based approaches to compute a near optimal resource allocation in a short period of time. Naturally, the reduced computational complexity comes with the cost of performance. The challenge then becomes to develop an algorithm that performs well under various network settings. We also plan on developing and implementing distributed algorithms. The goal here is to configure the entire network without relying on a central node. Each wireless domain controller negotiates with its neighbors iteratively in order to realize a near optimal allocation of spectrum and power in the entire network. The distributed implementation comes with a cost of performance and convergence time. The algorithm may take several iterations to converge to the near optimal solution. The challenge here is to develop an algorithm that performs well under various network settings. To reduce the transient cost of reconfiguring the network and also reduce the convergence time, we also consider algorithms that overcome local disturbances by reconfiguring a small part of the network. The wireless domain controller associated with this disturbance determines a small reconfiguration neighborhood and negotiates with its neighbors to realize a near optimal allocation. The local optimization reduces complexity with the cost of performance. Intuitively, the larger the neighborhood around the disturbance, the better the performance. So those are our plans for future work, and we thank you very much for your time and attention.